Hi, today we've got a question from step 1. It's a combinatorics one. It reads the following. Married couples sitting at a table, elementary probability C1. Alright, cool. 3 married couples sit down at a round table at which there are 6 chairs. All of the possible seating arrangements of the 6 people are equally likely. Show that the probability that each husband sits next to his wife is 2/15. Now, since we're dealing with people in pairs, it's best to model them as a block. I'll show you what I mean by this. So let's imagine we've got a round table. It's not round. It's a bit better. Still not round. So we're trying to make it so that let's call everyone husband 1, husband 2, husband 3. And we've got wife 1, wife 2, wife 3. So obviously husband 1 and wife 1 are a couple, so we can put a box around them. Husband 2 and wife 2 are a couple, and equally husband 3 and wife 3 are a couple. So since we want to have them seated with their blocks like such, so we've got, let's call this 1 for couple 1, 2 for, it's not very block, 2, and then 3. Now this is just one way of arranging the couples. So what we need to find out is all the possible ways of arranging these couples modeled as blocks around the table. And another thing we need to factor in is how they are seated. For example, we can have husband 1 there and wife 1 there, or we can have wife 1 here and husband 1 there, so we need to factor that in. So let's start. So first we should look at how many ways we can arrange these pairs or couples around the table. The way we do this is using the formula for arranging entities around a circle, which is n minus 1 factorial, and that is 3 minus 1 factorial in this case, so that's 2 factorial, which is just 2. So we're saying there's 2 ways of arranging our pairs around this table. Now you'd probably think, why is it not 3 factorial? Well, let's try this. So if we have couple 1, 2, 3, and another way we can arrange this is 1, 3, and 2. Notice if we're working clockwise, we go 2, 1, and 3, and then back to 3. You have 3, 1, and 2, then that goes to 3. So that is our possible combinations. But the question arises, why isn't 1, 2, and then 3 there? Like, if you look at this from a bird's eye view, this is and isn't the same. Well, the reason it is the same is because when we work clockwise, we go from couple 1 to 2 to 3. All it is that they have been rotated. So what this minus 1 does in n minus 1 factorial, it deletes the ways of rotating. It deletes the extra combinations that have been made by rotating the table. So we can say that these two are equivalent. And this n minus 1 factorial formula will be used for later. So we said there's 2 ways of arranging the blocks around the table. Now we need to consider how many ways there are to arrange the people within, or the husband and wife within the couple. So for block 1, or pair 1, we have 2 ways of arranging the husband and wife. Same for block 2, same for block 3. And then the total amount. So we're trying to figure out the total amount of ways to arrange the people. Well, there's 6 people. And like we said, the formula for arranging around a table is n minus 1 factorial. So 5 factorial, which is 120. So if we calculate this, we have 2 times 2, 4 times 4, 16 over 120. If we divide this by 4, 4 over 30, we can further divide, get 2 over 15. And that's as simple as we can get, so that is our answer. We know this is right because this was a show that question, so good start. I think this idea we've used to go about part 1 will probably be used later on, knowing the way step questions are. Right guys, on to the next part. Find the probability that exactly 2 husbands sit next to their wives. Alright, so there are a few cases we can consider here. Let's write them down, cases. Case 1, we can say is when we have couple 1, couple 2 together, and then we have husband 3, wife 3 on their own. Cool. Case 2, let's take couple 1, couple 3, and we can have H2 and wife 2 on their own. And for the third one, pair 2, pair 3, husband 1, husband 2. Now we know that the probability for each of these is equal. So all we have to do is work out 1 and times it by 3. So let's just solve case 1. So we need to arrange couple 1, 2 and husband 3 and wife 3 in a way so that husband and wife 3 do not sit next to each other. So since it's 4, we can simply split the 2 single beings by the couples. So we have couple 1 here, couple 2 here, and then we can have H3, wife 3. Now that we've got a general structure, we just need to think how many ways can we arrange them. So we know that there's 2 ways of arranging the 2 in pair 1. So 2, we're going to have a times 2 actually. Again, there's 2 ways of arranging the husband and wife in the second pair. So that's fine. Now, husband 3 and wife 3. Well, again, we can arrange these dudes, or guys, girls, whatever. We can arrange them in 2 ways. Why is this? Well, H3 can either be here or they can be here, and if Y3 can be here or they can be there. So that's just 2 ways across it. So let's draw that on. 2 ways. So if we find the probability of case 1, we have, so we know the total ways of arranging all the people is 120 from the previous part. So we have 2 ways of arranging pair 1, 2 again for pair 2, and again 2 for arranging well, the third pair. Not really a pair, but they are. Cool. It's got 8 over 120. Does 8 divide 120? Yes, it does. It goes in 15 times. And then we have 1 over 15. So like we said, this was just case 1. So we figured that worked out to be 1 out of 15 chance. So all cases must be 3 times probability of case 1. That's case 1, case 2 and case 3 are equal. 3 times 1 over 15, which is simply just 1 over 5. Nice. Right, part 3. Find the probability that no husband sits next to his wife. Sorry if it sounds like I'm out of breath, just come back from the gym. But anyways, find the probability that no husband sits next to wife. Let's just depict what this question is actually saying. So we've got no husband sits next to his wife. Well, if we take the negation of this, Well, the negation of no is at least 1. So at least one husband is next to his wife. Now you may be thinking, why have I chosen to use the negation? Well, the thing is with the negation, we know that probabilities sum up to 1. So if you take a statement and we take its negation plus negation, we know this equals 1, and that means so this question equals 1 minus probability of negation. And well, why negation, not just actually compute part 3 how we should? Well, if we look at the previous parts, we have the probability that every husband sits next to his wife. We've got the probability that 2 husbands sit next to their wife. Now we're just missing 1. The probability of 1 is sitting next to their wife. So at least 1 corresponds to probability of 1 pair minus probability of 2 pairs minus probability of 3 pairs. Now let's just sub in what we know so far. Actually, let's write this a bit more clearer. Let's put that over there. Probability, no pairs, let's call it that. So the current unknown is probability of 1 pair, so we just leave that as is. Probability 2 pairs, well, we just found out that that was 1 over 5. And probability 3 pairs was, I believe, 2 over 15. Yep, so minus 2 over 15. So what do we need to do? So 15 over 15 is 1, minus 3, minus 2, minus probability of 1 pair. 15 minus 3, 12, 12 minus 2, 10, 10 over 15, which is just 2/3, minus probability of 1 pair. Right. Okay, find the probability that no husband sits next to his wife. So the last thing we need to find is the probability of 1 pair. Let's bring in our circle again. And again, we have 3 cases. So case 1, when our only pair is 1, 2, let's copy this across, then only pair is 2, that's our second case. Case 3, only pair is 3. So let's just take case 1. Let's box that off. Bring this slightly down. So let's lock pair 1 in this position. So we have the task of arranging well, actually, let's quite a limited space. Let's bring it down. Right, case 1. We have the task of arranging husband 2, wife 2, and husband 3, wife 3, H2, H3, wife 2, wife 3. So we know H2 cannot be next to W2 and H3 cannot be next to W3. Fine. The way I like to think of this is, now that we've got this pair fixed in a position, we can almost see this circle as a straight line. So let's draw this circle as if it was opened up. So we're drawing the diameter, and then we draw pair 1 here. Now we just need to arrange these 4 elements or people along this line where husband 2 is not next to his wife and husband 3 is next to his wife. So we've got a gap there, a gap there, a gap there, and a gap there. Well, let's make all the husbands circles and all the wives crosses. And let's just think generally. So we know that no husband can be next to his wife. So there's a few ways we can think about it. I'm just going to try to list out the different ways of filling in this arrangement. So we can have it so that we have a wife, husband, husband, wife. That's one arrangement. We could have a husband, wife, wife, husband. We can also have husband, wife, husband, wife. Or we can have wife, husband, husband, wife, husband, wife. Now, we need to be careful here because we haven't actually labelled which husband and which wife are which. So let's take this example. Let's take the first case. So we've got wife, husband, husband, wife. We need to make sure that these two are not the same number, and these two are not the same number. How many ways can we do this? Well, we can have, let's write second wife there, third wife there, third husband there, second husband there, third wife there. That's one way. Or we can have third wife, second husband, third wife, second husband. Again, that works. So for this arrangement, we have two ways. And similarly, for this one, well, these are somewhat symmetrical, so we can say two ways again. Now we've checked for this. So if we have wife 2 there, we can only have husband 3 there. Then we can only have wife 2 there, husband 3, or the converse, 3, 2, 3, 2. There's no other ways we can arrange this arrangement. Sounds confusing, but yeah. So we've got two ways. Now let's take the last example. Well, it's somewhat symmetrical to the example before, so we can say two ways. So in total we found 8 ways. We're not timesing, we're just adding these cases because we sort of split case 1 into smaller subcases. So instead of timesing, we're just adding. So we have 2 plus 2 plus 2 plus 2, and that gives us 8 ways. Now remember, since we have got a pair, we have to always count the arrangements within the pair. So husband 1, wife 1, or wife 1, husband 1, so that's 2 ways. And now we've got all the information for case 1. So we can say case 1, so probability of case 1 is 2 times 8 over 120, 8 over 160, well that is 1 over 20, so is it? No, 16 over 160, 1 over 10. Cool. Hold up, I've made a mistake. It's not over 160, it's over 120. 6 minus 1 factorial ways. 16 over 120, which simplifies to, well, what can we divide by? Can we divide by 16? I don't think so. Let's divide by 8. 16 divided by 8 is 2. 120 divided by 8 is, I've done this before, 15. Right. And like we said, there were 3 big cases when it came to part 3. So probability of all 3 cases is simply probability of case 1 multiplied by 3, since all the cases bear the same result. So that is 2 over 15 times 3, which is 2 over 5. Nice. So we've found the probability that only one pair or couple are next to each other. So let's continue with this equation. So probability no pairs equals, what would we have? We had 2 over 3 minus probability of one pair. I should quickly say that all 3 cases is the same as just probability of one pair. We can use these interchangeably. Should have been more consistent throughout, but all good. So 2/3 minus 2 over 5. Let's get the denominators the same. So 15, 2 times 5 is 10. 2 times 2 times 3 is 6. So 10 minus 6 is 4 over 15. And voila, 4 over 15. Fun probability question. And I also liked how each part was quite helpful in the following. Like, we had to consistently use the idea that we can arrange the people within a couple, and that arrangement was 2 times. And it was also nice how we didn't actually have to find the probability that no husband exists with his wife. We could have just used information from the last few parts and then just a small calculation. We got a really nice result. So happy with this question. First set combinatorics question under my belt, and I hope to be posting more soon. Goodbye.